LearningMeasure.tv, a science and engineering podcast with emphasis on measurement, brought to you by David Archer and LearningMeasure.com. Episode 47, Temperature and the Volt. Hello, I'm David Archer, owner of LearningMeasure.com and LearningMeasure.tv. LearningMeasure.com is a subscription-based training website where you can get access to all the courses in the course catalog for $5 a month or $60 a year. If you'd like to try some of our courses are free. You can try the courses out and then decide whether you want to subscribe. I'd like to announce the following course being added to the course catalog, Physics 51, Introduction to Position, Velocity, and Acceleration. In that course, we talk about this obviously position, velocity, and acceleration, and introduce some of the concepts from calculus that are used in their definition. This is going to be the second of a series of basics physics courses that will have some emphasis on measurement. Okay, in the last several episodes, we've been talking about temperature. In particular, we were talking about if you have some thermometer, has some thermometric property X, one can create a temperature scale for that thermometer through this equation, where you take the temperature at some standard temperature and the value of the thermometric property at that temperature to calibrate this particular thing. Well, this does not give you thermodynamic temperature, what we talked about last week, which was temperature defined in terms of a constant volume gas thermometer. Well, as you can imagine, you wouldn't want to use a constant volume gas thermometer for doing most temperature measurements. It's tough to use. It will take a while to make the temperature measurement. So how do you make temperature measurements? Well, obviously you calibrate other standards. Well, the first thing you do is the Kelvin scale is defined in terms of the triple point of water and absolute zero. We've talked about that before. And then thermodynamic temperatures are defined in terms of that constant volume gas thermometer and the Kelvin, definition of Kelvin. Now, one thing about the triple point of water and other phase transitions of materials, they happen at well-defined temperatures and pressures. So even if we don't know what they are, we now have a temperature scale. And what we can do is take catalog and determine the actual thermodynamic temperatures for a series of phase transitions in materials. For instance, like the melting and points of metals, the boiling point of liquids, certain other types of phase transitions which all occur at specific temperatures. One can use something like a constant volume gas thermometer and maybe a few other means to determine thermodynamic temperature of those particular phase transitions. You can call those fixed points, and that's what they're called in what's called the ITS 90 temperature scale. A series of temperatures were defined based on phase transitions of materials that determine a temperature scale. That temperature scale is close to being revised again, but right now, 1990 was the last time it was revised with careful measurements and international agreement on what the temperatures of these fixed points are. So then what you've got to do once you've got these fixed points, you have to have some mechanism of interpolating between them. So if you have some thermometric property X, the thermodynamic temperature is going to have some functional relations to that property. Okay, it's not going to be just a simple ratio, because now we're not talking about a temperature scale relative to that thermometer. We're talking about a temperature scale excuse me, with respect to thermodynamic temperature. So, and typically what is done is the relationship is done with a polynomial, which is of this form. So the act of calibrating the thermometer is determining what these constants are. And that's done by measuring this property at a known fixed points and then doing some sort of least squares fit or some other type of fitting procedure to come up with constants to determine thermodynamic temperature with whatever you're using to interpolate temperature. Now, there are all kinds of things that you can use, and one of the things you can use is resistance. And a common laboratory type instrument to measure temperature is something called a platinum resistance thermometer. And for that device, the resistance is a function of temperature. You can use fixed points to come up with coefficients in a polynomial to, in fact, in a lot of cases it's predefined for a platinum resistance thermometer, and that can be used as a standard to calibrate other thermometers such as a mercury and glass thermometer or some other time. But I want to talk about something a little bit different first. There's this guy by the name of Seebeck who made this discovery about metals, that if you take metal, let's say a metal wire, and at one end you heat it in some manner, okay? So there's a temperature difference between the ends of the metal. Well, the electrons in this end, you can think of them as a gas, right, are heated up. They're moving around. And they're not moving around so much over here. So you could kind of imagine that on the average there might be more electrons on one side or the other. So there's a voltage across this thing that depends on the temperature difference. Okay. So, okay, that's fine. How does that help? Well, you have to measure that voltage somehow. And to measure that voltage somehow, you got to put some sort of meter in there, right? Some sort of voltmeter, you know. Well, to do that, you could hook one end directly up to the voltmeter, but you got to get some sort of terminal down to the other end. Well, that's okay. We put that wire down to the other end, connect to the other end, we try to measure it. Well, if you do that, this wire will have a temperature difference across it too. It'll be at the same temperature there. So if they're made of the same material, the same voltage is going to come across this wire. And you're going to measure zero. Well, what Seebeck discovered, basically, and others, was that fortunately, all metals don't behave the same way. So this temperature difference, let's say, call it V1 for this metal. If you put a different metal, it's going to have a different voltage as a function of the temperature difference. So what you're going to measure here, basically, is V2 of the temperature minus V1. So what you're going to measure is the difference. Well, you need to know the temperature at this end, and then, you know, there's your meter sitting here, who knows what's going on. So, but this is called, what this is called is a thermocouple. A thermocouple is basically two wires made of different material that are connected, and they have a temperature difference across them. Well, this is a small voltage for most things. There's another thing you could do. Let's say you could take a thermocouple, two different wires joined here, and you have some sort of flame or temperature difference, right? You could put one end heat one end, and you take the other end and like put it in like an ice bath or something. Okay, now there's a known voltage difference across that wire. Well, now what you can do is, well, you can hook wires here. Now, if these wires are the same, there's going to be no thermocouple. There's going to be no temperature-induced voltage difference here, but there will be here. And you could, you could continue this on. You could do more wires, but that's not what I'm going to care about. So anyway, you could come up with a precise method of measuring temperature with a thermocouple. But there's another thing you can do. We know that resistance is we know that temperature basically is related to energy or power delivered to a substance. In particular, resistor. If you take a resistor and you put some sort of voltage across it, there's going to be some current flowing into the resistor. Okay, the power that's going to be dissipated by that resistor is I squared R. We've talked about this before. So that turns into heat. It's dissipated in heat. Well, what happens if you take a thermocouple and connect it to the resistor, and you measure the voltage difference? Okay, well, this temperature, the temperature dissipated in the resistor is the power delivered to the resistor is going to definitely produce a voltage because there's going to be a temperature. This is going to be hot. And what one does is make something like this and encases it in some sort of glass enclosure. And this is called a thermal element. And it's used to measure voltage. Because when you determine the current, you can determine the voltage through Ohm's law. So if you have some DC voltage, this is also generally put in a can. That's made of some sort of thing to thermally insulate it from the outside world. And usually there's some sort of coaxial connector at the top, or how should I draw this? Up at the top. And so what happens is, okay, so this case is grounded somehow. And what happens is that you put some sort of voltage between here and here. Now, how should I draw that? You put some voltage here. It'll heat up the resistor, and it'll result in some sort of indication here because there's going to be some heat there. This is called a thermal voltage converter. So you go from temperature measurements to voltage measurements. Now, DC measurements are well known. We have a precise way of generating DC voltages. What this is used for is AC and RF voltages. And so what you do is you first put in a DC voltage and you measure the output voltage. Or you do it the other way. You put the RF voltage in or AC voltage in. And then you measure whatever, you adjust the thing so that you're always measuring the same voltage out the thermal converter. So that you get the same amount of heating for the AC voltage or the RF voltage as you do for the DC voltage. Now there's some complications, like you have to measure both polarities of the DC voltage and average them, because there's some effects in here where you could have some differences based on like where the thermocouple is actually joined to the resistor, among other effects. So what you generally do is you put in some AC voltage or RF or whatever, and you note some voltage here. Let's see, we'll call it TAC. And then you're going to reproduce that. Well, let's just call this V. That's VT. Then you're going to put in a V plus to reproduce that number, and a V minus to reproduce that number. Well, then you come up with a voltage, average voltage, which is V plus, absolute value of V plus, absolute value of V minus over 2. We'll call that VDC. Okay. So there's going to be a difference between these voltages if you knew what they were. And what would be VAC minus VDC over VDC. Okay, which could either be called the AC-DC difference or the RF-DC difference. So if you wanted to get the actual AC voltage then, and you knew the RF-DC difference, it's going to be VDC plus delta times 1 plus delta. So you somehow calibrate the AC-DC difference, and then you trace voltage measurements directly through temperature. And that often happens in measurement, where you will actually trace one quantity through another. Now, you don't need to know what the temperature is. All you need to know is it is the same temperature for each of the measurements for this to work. So temperature measurements can be used to determine voltage measurements. They can also be used to measure like optical power or any other thing. So that's kind of fundamental in that way. Anyway, then once you have this thing, one of the things you can do, there's only a narrow range where these things can be used. Range of voltages, I should say. So what you do is you create what's called a voltage divider. So what normally they do is they build something like we were saying before. You put your excuse me. So you put your thermal element in there. And your thermocouple output. There might be another resistor in here. And then what they sometimes do is they make what are called range resistors that you attach to this thing, which has some other precision resistor in there to change the voltage dividing so that you can use that to cover a wider range of AC or RF voltages. Now, this is normally done for AC voltages. For RF voltages, generally there's a built-in, because at this point you have to put in a T of some sort, generally. And you would do a bunch of to do the calibration, you have some DC standard and AC voltage put in there maybe, just to make it go faster, or you might do something else. But what generally happens with the RF ones, because of transmission line effects, they'll generally build in some sort of T. Yeah, I'm not the best artist in the world. So that there's usually a built-in T. Because you also have to worry about transmission line effects. So you want the geometry held, because you're talking about a device that's large compared with a wavelength generally. Well, and you don't want to change the dimensions much. So most of the RF ones are built-in T's and are used as sources. Now, these things are very fragile. You only want to use them like the constant volume gas thermometer. You only want to use them in labs that do calibration of other instruments that would be used to make more practical measurements. But they are a very accurate way of measuring AC and RF voltages. Now, at some point you can't use these anymore for measuring voltage. Basically, once this distance here between, like the edge of the container and the position of the thermal element is like a quarter of a wavelength, this could conceivably be at a null in a standing wave pattern, and it would be totally useless. Many of the RF types can go up to maybe a gigahertz. Some of them claim that they can go to 2 gigahertz. The highest I've ever heard of someone even attempting anything was 4 gigahertz, and I don't know how good that would be. So you're really pretty much limited to 1 gigahertz and below for this type of standard. And there's all kinds of other technical issues, but I thought it might be interesting to talk about this a little bit. All right, that's it for this episode. Again, if you have any suggestions for episodes, just send us an email at suggestions@learningmeasure.tv. Or if you have any questions, send us an email at questions@learningmeasure.tv. That's it for now. I'll see you next time.